So we started out, and this is all a review from petrophysics. So I know that you learned all this in Dr. Sharma's class. Maybe you use different nomenclature at times, but you did learn this. So the multi-phase version of Darcy's law can be written in any of these ways, and they're all the same. So U is the Darcy velocity, okay? And in general, that's a velocity vector. It can have an x, y, and a z component. If it's only in one dimension, then it's just U. It's a scalar. But you can have 3 dimensions, and that's why it's a vector. And usually I write it as a column vector. I wrote it as a row vector, but then transposed it, which makes it a column vector. Now, what does the J subscript indicate? The J subscript indicates that J is the phase. So that could be W for water, O for oil, or G for gas. You can have a water velocity, a gas velocity, and an oil velocity. K is the permeability tensor. And a permeability can be anisotropic, which means that the permeability in the x direction is different than the z direction, is different from the y direction, which is why we have a 3x3 tensor here. I should note that there's a diagonal elements and there's off-diagonal elements. It is symmetric, meaning that kxy is equal to kyx, kxz is equal to kzx, and kzy is equal to kyz. That's the permeability tensor. Now, we almost never use a full tensor. We often approximate it by a diagonal tensor. You can actually reproduce this by turning your axes. But so we might have an x, a y, and a z component of permeability. We won't have a full tensor there. And then if it is isotropic, if kx is equal to ky is equal to kz, then we just get k as a scalar. And many times in this class we'll do that. Many times in this class we'll do that. What is grad p? Okay, so I know myself, I often get intimidated by these del operators, and I would imagine many of you do too. The del just indicates that it's a vector, it's a divergence, it's a derivative. Okay, so del p of j being the phase, is the derivative of p with respect to x, derivative of p with respect to y, derivative of p with respect to z. So it's just shorthand notation for that. And the other nice reason to do that is that even though we're dealing with Cartesian coordinates for now, this could be in cylindrical coordinates. So you could have an r, theta, and z component. What is h? H is the elevation. And I mentioned last time that elevation is positive as you go up. So as you go up a mountain, the elevation increases. And so del dot h is again a derivative dh dx, dh dy, and dh dz. Okay, and if it's at an angle, then then dh h is not equal to z. It could be in that direction there. D is the depth. It's the opposite of elevation. So D increases as you go deeper. So as we go down into a reservoir, I say that the elevation is negative 5,000 feet, but the depth is positive 5,000 feet. I like to use depth. And because of that sign difference, we have a negative here rather than a positive. Otherwise, these two equations are the same. And then the potential has units of pressure. It's got units of PSI or pascals. In the absence of gravity, if you just had a flat porous medium with no change in depth, then the potential would be equal to the pressure. But if you do have a change in depth, then potential is essentially a corrected pressure, corrected by gravity. And so it's pressure minus these the gravitational terms. So one thing I didn't mention on here is this KRJ. That's the relative permeability, R, of phase J. And it's a number between 0 and 1, and I'll cover that in just a moment. Okay, so that was multi-dimensions, multi-phase flow in multiple dimensions, 2 or 3 dimensions. But let's talk about a special case, and a special case that we'll be talking about for the next several weeks, which is just one-dimensional flow. So it can be 1D, but it can still be at an angle, and that's why I've drawn this over here. So there is a dip angle. and then it's one dimension in the x direction. We just have to draw a coordinate system that way. So you can rewrite the multiphase form of Darcy's law this way, where u is the velocity of phase j. It's only one direction, so it's not a vector anymore. It's just one velocity. Krj is the relative permeability. K is the scalar permeability. There's no permeability tensor because it's in 1D. Mu is the viscosity of phase j. This is the pressure of phase j, so the derivative of that. Rho is the density of the phase. And of course, alpha is the angle. So if you notice, if alpha is 0, then the sine of 0 is 0, and this whole gravity term goes away. So if it was a flat, then that would be the case. If alpha was 90 degrees, it would be completely vertical, and then the sine of 90 would be 1. So if we rewrite this equation, Darcy's law, for two phases, water and oil, we could have gas as well, but a good portion of this class I'm going to be talking about just water and oil. Then you could write this over here. So all I did is I took this equation, and for J I substituted W or O. It's important to remind ourselves that the pressure of the water phase does not in general equal to the pressure of the oil phase. The difference between PO and PW is called capillary pressure. You learned about this in petrophysics. So PO is not in general equal to PW. Many, many times in this class, I'll make the assumption that they are, though. And I will tell you, or I'll tell you that they're not equal, or maybe you'll have to make an assumption and say that they're equal if I don't specify otherwise. But in general, PO is not equal to PW, and PC is a function of saturation. Also, you could take the derivative of this, so dPc dx is equal to dPo dx minus dPw dx. And again, I won't talk much about this, but I do talk about it in the petrophysics review video if you're interested. Capillary pressure is a function of water saturation, and you have these two endpoints, which are the irreducible or residual water saturation and the residual oil saturation. You have no flow below the residual water saturation or below residual oil saturation. So let's talk about relative permeability. That's that Krj term. And that's really important for multiphase flow. It's really this single variable that converts Darcy's law in single phase to multiple phases. So what it is, it's a correction to Darcy's law for multiphase flow. Krj is equal to Kj over K. K, the denominator, is again the single or absolute permeability. And Kj is the permeability of the phase. Now Kj will have units of permeability like millidarcies. But if you divide Kj divided by K, we get a dimensionless value, the relative permeability of phase J. So Krj is dimensionless. It is always less than or equal to 1. Okay, so it'd have to be, there's probably very, very weird situations where it's greater than 1, but for our purposes, it's always less than 1. And the sum of the relative permeabilities of all phases is less than or equal to 1. So KRW plus KRO, if we have two phases, is less than or equal to 1. Or if you have a third phase, then they would all equal to less than or equal to 1. Importantly, it's a nonlinear function of saturation. So, and you could use either the water saturation or the oil saturation. I'll normally refer to the water saturation, SW. But Krj is equal to 1 if the saturation of that phase is 1. Well, what does that mean? If the saturation is 1, if you have 100% water, then that's just single phase flow. In which case you don't have multi-phase flow anymore, in which case this is just 1 and you get the regular single phase Darcy's law. If the saturation is below the residual saturation, so if SW is less than SWR, then that goes back to the comment I just made on the previous slide, that water is not moving. So if the residual water saturation is 20% and the water saturation is 19%, then that water is not moving at all. That means the velocity of the water, U sub J, should be equal to 0. And what that means is that the relative permeability of that phase is 0. Otherwise, it's going to be some function of saturation, and I'll show you what that is here in these in future slides. There are different ways to do measurements of relative permeability. I don't want to focus too much on this, but one of those methods is called the steady state method. In the steady state method, you inject your oil and water at specified velocities which give you a saturation, and then you measure the amount of oil and water that come out at the other end. And once you get to this steady state, and you can calculate the relative permeability from Darcy's law using your pressure gradient and your known flow rates, and back calculate relative permeability. The other technique is called the unsteady state method. In the unsteady state method, what you have is you have a core that's probably saturated with oil and irreducible water, so maybe something like 20% water, 80% oil. Then you inject water and it displaces that oil, and as time goes on, the water saturation will change with time, the pressure drop will change with time. You can back calculate relative permeability as a function of time or as a function of saturation. That's what makes it unsteady state, is that the relative permeability and everything is changing with time, and you collect all those points. That's faster and it's more common because it's really just one experiment. You start out with oil, maybe a little bit of water, then you inject water, and you do one experiment with time, and then you're done. With the steady state method, you have to do an experiment at a specified oil and water rate. You wait a certain amount of time, you get your answer, then you have to restart it over again and change your ratio of QO to QW. But that's how you measure relative permeability. Again, you inject rates, you measure the pressure drop because you're going to have pressure gauges on these, and you back calculate. You would have measured the permeability in advance, so then you just back calculate relative permeability from Darcy's law. Okay, so what does a typical relative permeability curve look like? You should have seen this before. This is relative permeability versus water saturation. Normally we put water saturation on the x-axis. We could put oil saturation. As a reminder, the sum of saturations has to equal to 1. So if you have just water and oil, then SO is 1 minus SW. Because if you've got 30% water, then you must have 70% oil. This is a water-wet medium. I know this, and I'll tell you why in a second. By the way, there was a typo in the original slides, and that's why I've changed this to oil and this to water. And I put that in red. And I'll fix those at a later time, but you might want to make a note of that if you've downloaded these slides. A few things to note. So I'm going to start with the water. So it's this solid line here. You'll notice that the relative permeability between less than 0.2 is 0. Okay? Because of that, I know that the residual or irreducible water saturation is 20%. Because anything below that, the water doesn't move. The velocity is 0, the relative permeability is 0. But as I increase the water saturation, the relative permeability increases as well. And it gets to this point right over here, and this is the 1 minus the residual oil saturation. So kind of a coincidence here, but the residual oil saturation is also 20%. But typical values are anywhere from 5 to 25%, 5 to 30%. For both, for water and oil. Okay, but if you notice that when it gets to this point, it's less than 1. So at this point right here, and I'm going to call this, okay, well let me just go back. This is the residual water saturation. This is 1 minus the residual oil saturation. This point here, I'm going to call the endpoint water relative permeability. So KRW naught. That number is going to be less than 1 for a water-wet medium, And the reason is that I've got, at this point, it looks like 80% water and 20% oil. Water, the wetting phase, occupies the smallest pores, which have the least amount of permeability. So even though they occupies 80% of the volume, the 20% that's occupied by the oil is occupying all the good permeability. And so the relative permeability of water is much less than 1. On the other hand, if we look at the oil relative permeability, if we're above 0.8, basically if the oil saturation is less than the residual oil saturation, again it doesn't move. And we have to remember that the rest of the semester, is that if the saturation of a phase is below its residual saturation, then it is immobile. It does not move. The velocity is 0, the relative permeability is 0. But as the oil saturation increases, or the water saturation decreases, same thing, this goes up. And then here at the residual water saturation, you'll notice that the oil relative permeability is close to 1. Probably not quite 1, but it's close to 1. Why is that? How can it occupy 80% of the volume, but the permeability is almost 100% of what would be in single phase? Again, that water, that 20% water that's occupying is really the really small pores, which contribute almost nothing to permeability. And so that's why this is the case. Now, this is for a water wet medium. If it was an oil wet medium, it would be reversed. If it was a mixed wet or intermediate wet medium, you'd have something in between where maybe the endpoints were both somewhere in between, 0.4, 0.5, 0.6, something like that. This is KRO naught, the endpoint oil relative permeability. Okay, so what we do is we do those experiments that I referred to before, and with those experiments we can create these plots. What we normally do is we fit those plots to equations, correlations that are easier to use. A common one is the Corey-Brooks model. The Corey-Brooks model looks like this. It says that the relative permeability of water is equal to the endpoint relative permeability of water times some normalized saturation S to some exponent NW. Now NW is always greater than 1. It's usually less than 3. 2 is a typical number. KRO is the endpoint relative permeability of oil times 1 minus the normalized saturation to some exponent NO. And again, NO is usually different from NW, but it's between 1 and 3. What is S? Okay, I called it this normalized saturation. I normalized it by the residual saturations of water and oil, so SWR and SOR. So S is equal to SW minus SWR divided by 1 minus SWR minus SOR. What does that mean? If SW is equal to SWR, so if SW is equal to this, in this particular case 20%, then S is 0. If SW is equal to 1 minus SOR, if it's this number right over here, then S is 1. So that means that S can go from 0 to 1 in between the mobile regions, so in between here and over here. So it normalizes it by these residual saturations. Okay. And again, these empirical coefficients NW and NO are greater than 1 and usually between 2 and 3, or at least between 1 and 3. So we might do some practices with this on Friday or something, and probably be in your homework. We have oil and water flowing through this. And what fractional flow is it's exactly what it sounds like, the fraction of the flow that's a specific phase. So I'm going to use the term F J. So F for fractional flow, J for phase. And Fj is by definition Uj divided by U total. U total is the total velocity. So if my velocity were 2 feet per day and the water velocity was 1 foot per day, then the fractional flow would be 0.5 or 50%. So Fw is the fractional flow of water, which is the velocity of water divided by the total velocity U. And Fo is equal to Uo divided by U. If I had gas as well, then Fg would be Ug over U. For the purposes of today, I will stick to mostly two-phase flow, water and oil. So, if U is the total velocity, it is going to be equal to the sum of the velocity of all phases. J is equal to 1 to Nj. So if UW is 1 and UO is 1, then U total is 2. If UW is 0.5 and UO is 1, then U total is 1.5. So it is going to be equal to UW plus UO. And if I had gas, it'd be Ug. Okay. Of course, if there's no gas, then Ug is 0. Okay, so this is an important equation. So U is the sum of the phase velocities. And another important equation is that the sum of the fractional flows, J is equal to 1 to Nj, so Nj is the phase, is equal to 1. So that kind of makes sense, right? So if it's, let's say the water velocity was 1 and the oil velocity was 2, then the total velocity would be 1 plus 2 is 3. So the fractional flow of water would be 1 divided by 3, 1/3. Fractional flow of oil will be 2/3. Right? So 1/3 plus 2/3 is 1. So this is important. The fractional flow of all phases has to equal to 1. Now, one thing that is a little confusing is that fractional flow can be less than 0 or greater than 1. Now, how is that possible? Well, the way that that's possible is what's called countercurrent flow, and I'll return to that later on. So you could have the water velocity being positive and the oil velocity going the other way being negative. And so the sum is going to be a positive plus a negative. And so you could have the fractional flow of one phase be negative and the fractional flow of the other phase be greater than 1. But when you add the two together, you'll get that. And I'm going to return to that because it is a little confusing, and I'm going to explain when that happens. But a little bit of foreshadowing, it happens when gravity is important. Okay, because water is usually heavier than oil, and because of gravity, even in the absence of velocity, it's going to want to go down towards the bottom. But we'll revisit that, but I just want you to recognize that the sum of all fractional flows is 1, but you could have negative values and values greater than 1. Importantly, fractional flow is a function of SW, but not, at least in general, not equal to SW. And this is a place where a lot of people make mistakes. If I told you that, well, we had 70% water and 30% oil, and I said, well, what's the percent of the flow that's water versus oil? Some people might say, well, it's 70% the fractional flow of water, but they would be incorrect. Fractional flow of water would probably be a lot closer to 100% because that oil is almost immobile, or might be immobile if the residual oil saturation were 30%. So we'll derive some equations and show why that's the case. So that F is a function of SW but not equal to SW. Okay. By coincidence, there might be some cases where they're equal, but in general, that's not the case. So to derive this, let's recall Darcy's law. Uj, that's a velocity of the phase, and I'm going to do it in 1D. Darcy's law in 1D is minus K, KRJ, that's the relative permeability, divided by the viscosity of J, times dpj dx plus rho g sine of our dip angle. That's Darcy's law in multiple phases. And we could write J is equal to W and J is equal to O, and I'll do that. So I'll say for two-phase oil and water, I'm going to rearrange this a little bit. I'm going to bring this over here and bring that on the denominator, and I'll say that minus UW times mu W divided by KRW. So my velocities and viscosities look similar probably. U is the velocity, mu, the Greek letter mu is viscosity, is equal to, and I'm going to say that mu W is just minus F W UW K over KRW times U, right? Because UW is the fractional flow times the velocity. That comes from this up here. So the velocity of a phase is equal to total velocity times the fractional flow. And that's going to equal to this right-hand side, which is dpW dx plus rho W g sine alpha. I'm going to do the same thing for oil. Minus UO, U oil, K over KO oil is equal to, now I can say minus FO, but I know that FO plus FW is 1. So I'm going to put 1 minus FW there. And that way I only have one variable, FW. So if FW plus FO is equal to 1, then FO must equal to 1 minus FW. And that's equal to dPO dx plus rho O g sine alpha. Okay. So I just rewrote Darcy's law. That's all I did. I took this equation over here, I moved some things over, and I replaced the phase velocity with the fractional flow of the phase times the total velocity U. Otherwise, this is just water and oil. Oh, I do have a mistake there. This was the viscosity of the oil. This is the relative permeability of the oil. Otherwise, that looks good. Okay. Let's see if there's questions pop up. Not yet. So now what are we going to do? What we're going to do is we're going to subtract these two equations. Okay. I probably should have written this equation first and that one second, because I'm really going to take this one, subtract that one, but you could do it the other way, and you would just probably have to multiply a negative sign through for that. If I subtract this minus this, okay, so keep in mind that a negative minus a negative is a positive. What you'll get is something like this. FW mu W over KRW minus 1 minus FW mu O over KRO I'm just going to pull out the total velocity u over the permeability k is equal to dPo dx minus dPw dx. That's dPc dx, right? Because PO minus PW is the capillary pressure. And then I'm going to have rho naught g sine alpha minus rho w g sine alpha. And I'm going to write that as minus delta rho g sine alpha, where dPc dx is dPo dx minus dPw dx, and delta rho is equal to rho of water minus rho of oil. Okay, so let me make a few comments about that. The first one is you should try to derive that yourself. So if that went a little bit fast, you're not quite sure of it, it's just algebra. Spend a few minutes to try to do it. Rewatch the video a couple times if you need to, but try to reproduce this over here. dPo dx minus dPw dx is equal to dPc dx. That's why I wrote that over there. And then we had this rho O g sine alpha minus rho W g sine alpha. And I get this delta rho. And you might be wondering why I have a negative there, because this is a positive minus that. Why is that going to be a negative in front of the whole thing? The reason is I switched the densities. I said that delta rho is rho W minus rho oil instead of rho oil minus rho W. Why did I do that? It's just convention, but there's a reason for that convention, and that's because the density of water is almost always greater than the density of oil. So that makes delta rho positive, but then this is going to be minus that positive number. So again, I encourage you to work through that yourself. But we're going to do another couple steps here. We want to solve for FW. So I got an FW here and an FW there. I can move some things around, and this is algebra again, and I really encourage you to try to do the algebra yourself. I say FW times 1 plus KRO mu W over KRW mu O minus 1 is equal to KRO mu O times the total velocity U. Please work through that with yourself to prove to yourself that that's correct. Or if I solve for FW, I get an important equation, which is the fractional flow equation. Okay, so that's the fractional flow equation. And that why did I subtract this equation minus this equation as opposed to this equation minus this equation? I'm almost positive you could do either one. It's just that you would probably get extra negative signs everywhere, and they would be completely equivalent. So either way would have worked.